All right, we will go ahead and get started. Welcome everyone to our monthly PCAST talk series. We have just a very small amount of news before we get started, which is mainly just keep a lookout. We are all still waiting for the official NASA selection decision, which is anticipated to occur this fall, hopefully in September. So please just keep an ear out for news from us. We have more PCAST talks coming up this semester. So we have, in addition to today's talk on PI science, we have one more talk on PI science that will be happening in October. Andrea Benzatti will be talking about protoplanetary disk science. And then we will also have a number of community science talks this fall, most of which will be in a slightly shorter format. So we'll be having 2 talks each month, half-hour talks on a variety of science outside of sort of the PI science that has been conceived of by the community in advance of PRIMA. So today, of course, we're hearing from Irene Shivaei. So Irene is going to be talking about the PI science case for PRIMA, the rise of dust and metals. Irene is a PRIMA science affiliate and has been helping to co-lead our science working groups. So Irene, I will stop sharing and let you take it away.
Thank you very much. Let me start my presentation. Okay. Well, hello everyone. Thank you, Betsy, for the introduction. As said, I'm Irene Shivaei. I'm a researcher at the Astrobiology Center in Madrid, Spain. And mainly my day-to-day thinking is about dust properties in galaxies at cosmic noon and higher redshifts. So today, as one of the science affiliates of PRIMA, I'm going to talk about the science case of rise of dust and metals, the PI science of rise of dust and metals that is planned to be done with PRIMA. Many thanks. First of all, I want to say that a lot of the slides that I'm going to show are borrowed from multiple presentations by various members of the PRIMA team. So thanks in advance for that. First of all, a disclaimer. As I mentioned, I'm going to talk about mainly the PI science case on dust and metals with PRIMA, but there is a lot that can be done on this topic, given the unique and unprecedented capabilities of PRIMA. And that's very clear from multiple science cases that have been published in different issues of the Geoscience books, Volume 2 and Volume 1, which was published a few years ago, as well as the JTIS PRIMA special issue that was released last year. From the community, and this is how it should be. PRIMA, 75% of the time of PRIMA is for general observers. So there are a lot that can be done on this topic, and I just wanted to say that I'm not going to cover those, maybe just a small mention of a few of them, but this is a very specific talk on mainly focusing on the science cases for the PI science, but also I will be talking about the legacy values of those observations that can be used by the community. So first of all, a little bit of background just to make sure that we are all on the same page. Why should we care about dust? Dust by mass is a very small fraction of the baryonic matter in the universe. Only 1 part in 1,000 of the baryonic matter in the universe is composed by dust, but this small constituent is everywhere in galaxies. And in terms of energetics, it has a significant role in galaxy evolution and galaxy processes. For example, if you look at the SED of the universe, the cosmic microwave background dominates the SED of the universe. But if you look at the light that comes from extragalactic processes, galaxy formation and evolution processes, half of it is dust reprocessed starlight called cosmic infrared background. Also, if we look at the star formation activity in the universe, a large fraction of a star formation is in the form of dust-obscured star formation. This is the classical plot of evolution of cosmic star formation density as a function of redshift, where the green and blue lines, symbols show the unobscured star formation measured usually from UV light, and in red you can see the dust-obscured star formation rate, and you can easily see how significant its contribution is throughout cosmic time. And if we go to smaller scales, dust has very important and key roles in the physics and chemistry of the ISM. From star formation to being a catalyzer for formation of certain molecules like H2. It has key roles in cooling and heating of the ISM, in ISM gas dynamics, coupling the magnetic field to the gas, and the list can go on and on. So not only in terms of energetics, global energetics, but also in terms of the smaller scale and star formation and molecular formation in the ISM of galaxies, dust plays an important role. So whether you are an astronomer studying stars or studying formation of galaxies through designing large surveys, you cannot ignore the effect of dust. In addition to those, dust in general also shapes the way we see galaxies. If you look at the stellar emission of galaxies, we will have a very biased view of galaxy evolution, whether it's in a spectroscopy form or in imaging. The stellar emission is completely biased. When we add dust, the UV and optical emission becomes attenuated with a wavelength dependent function and emits in longer far infrared wavelengths. And this is very clear in both the SED that I'm showing on the left and the various images here. I'm just showing one of the images from JWST that shows a completely different picture of this nearby galaxy in infrared compared to what we've been seeing with Hubble in optical. So if we want to observe dust, the effect of dust, we can look either in the attenuation or in the emission. And the emission part has different components. The shortest wavelength in the mid-infrared, these are coming from molecules called PAHs, which I will be mentioning multiple times in the rest of the talk. The PAHs produce these broadband emissions in the mid-infrared. And in addition to those, we have this continuum emission at far infrared, which can be, in a very simple way, modeled as a modified black body with a peak that represents the typical temperature of dust, larger grain dust in the galaxy. So just continuing on the line of why we should care about dust in galaxies, we now know that dust exists up to very high redshifts as well. It's been observed both in emission and in attenuation out to very high redshifts. On the left, I'm showing one of the highest detections of dust continuum in a redshift 8 galaxy with ALMA. These are building on almost 2 decades of ALMA legacy, and it's amazing to have such a reservoir of dust at such early times. And on the right, I'm showing a couple of studies that look at dust in attenuation with the high sensitivity of JWST. So as I mentioned, to study the properties of galaxies, including dust, we need multi-wavelength observations to look at them throughout the cosmic time. I'm showing the same unobscured and total SED of a galaxy that I showed before, from redshift 0 local universe to higher redshift cosmic noon and entering the epoch of reionization. So to conduct such a multi-wavelength observations, I'm going to show that these are the facilities that we currently have. With Hubble and JWST at high redshift, we can mostly look at the attenuated properties, the rest frame UV, optical, and a little bit of the mid-infrared. And with ALMA, we are capturing the peak of the SED when we are going to higher redshift. And you can see that there is a huge gap between the current facilities, sensitive facilities that we have to study particularly high redshift galaxies, high redshift galaxies, the dust emission in high redshift galaxies. And this is where PRIMA beautifully come into play. So this is the wavelength coverage of PRIMA, covering the dust emission from redshift 0, PAHs at cosmic noon, all the way to very high redshift. So PRIMA is, as you probably all know, but as I said, I'm just going very quickly with some introductory slides, is a 1.8 meter telescope that is cooled to very low temperatures, 4.5 Kelvin, which is a huge advantage of it compared to the previous telescopes like Herschel. It has a state-of-the-art detectors, which bring a huge sensitivity gain for this telescope over the past decades. Over the past decades, the sensitivity of the technology of these detectors have improved a lot, and bringing more than 2 orders of magnitude in sensitivity compared to what Herschel had. The combination of its 2 instruments make it very powerful. PRIMA has a PRIMager imaging, which has a polarimetry imaging part, and a hyperspectral imager, which basically gives us a resolution of 10 spectra within its wavelength range. It also has a spectrometer, FIRUS, which gives us a spectrometry between a resolution of 100 to more than 10,000. And these are between the wavelengths of 24 to 261 micron. Where PRIMA is really different from from the previous telescopes is the sensitivity and the survey speed of it. It has more than, sorry, I think. Do you see my slides? I think I lost the.
No, we're just seeing a blank screen.
Okay, how about now?
Yes, good.
Okay, sorry, I got a message from Teams, but I need to stop it. Anyway, okay. So where PRIMA gains the most is its survey speed. So in this plot, you can see compared to Spitzer, IRS, Sophia, and Herschel, this is what we are going to get with PRIMA. The y-axis is the time to survey 100-degree square arc-minute of the sky, and on the x-axis is wavelength. So this is, as I mentioned, is PRIMA's superpower, the mapping speed. The combination of the fastest slew, steering mirror, and the large field of view of PRIMA brings very fast mapping. As an example here on the background, you see a simulated image of the wide field PRIMager image from 25 to 80 micron, and the spectra, FIRUS spectra of 2 redshift 5 galaxies. So these two together bring very powerful, very good opportunities to survey a large part of the sky and go for follow-ups with the spectroscopy. As an example, there was a GEO idea to do an all-sky survey that would go 100 times deeper than Akari, comparable to Herschel deep fields. So with all of these amazing capabilities, the PI science focuses on various scales, from solar system to cosmology, looking at planet formation, water in disks, black hole growth, galactic outflows, as well as metal abundances that comes from far infrared lines, PAHs, and many more. So in this talk, I'm going to focus on this last one, the buildup of dust and metals. The main goal of the PI science is to answer 3 questions. What is the origin of dust in the universe today? How, or in other words, how rapidly is dust homogenized by continuous cycles of destruction and regrowth in the ISM? How have dust and metals co-evolved over the past 10 billion years? Dust itself is a tracer of heavy elements that, as I mentioned, has a big impact on coupling of radiation and interstellar material, regulating the star formation, and generally shaping the output of galaxies. So the question is, while this dust is very closely coupled to metals, how have they co-evolved from redshift 0 to cosmic noon? And the last one, when and where did the first carbon nanoparticles emerge in the universe? This is an opportunity to look at the formation processes of dust and metals in the very early massive galaxies. So let's look at the first science case, the origin and structure of interstellar dust. So the key here is polarimetry. Using the polarization SED, we can understand the origin of dust grains. So here you see the polarization SED as a function of wavelength. This should rise very sharply with wavelength, the purple line, if the carbon and silicate populations are separated from each other. This is the classic dust model. You have the separate silicate and graphite grains. This is what would be expected from the polarization SED. However, the new picture of astrodust, where these components are all mixed with each other, predicts an almost flat polarization SED. So the idea is with PRIMA to look at, to directly test the scenario of ISM grain growth and see if it's suppressed at low metallicities in local galaxies by doing polarization imaging of a sample of 30 nearby galaxies. So what you're seeing here is a simulated image, the magnetic field orientation vectors that are overplotted on the far infrared emission of a nearby galaxy at two wavelengths, the 90 micron and 230 micron bands. So this amazing capability of PRIMA in comparison, for example, with SOFIA, brings deeper polarization maps by a factor of 100. Yes, as I mentioned, by measuring the polarization spectrum in the local universe over a range of metallicities, the idea is to constrain the evolution of dust from pristine stardust to ISM mixed dust. And this is the ratio of the two polarization at the two wavelengths that I showed before. And the idea of the PI science is to do this survey for a few tens of nearby galaxies. Now, moving on to the second science question, which is more the area of my own science, so I'm going to spend more time on it. How have dust and metals co-evolved over the past 10 million years? So here the idea is to use both the hyperspectral imaging and the far infrared spectroscopy to provide crucial diagnostics for dust emission from PAHs, as well as temperature insensitive fine structure lines that bring us as metallicity indicators. Here on the plot, you can see the SED of a galaxy from redshift 0 to redshift 5, and the PRIMA wavelength coverage that, first of all, at redshift 0, the science case that I mentioned before, you can see the polarized emission here. But as we go to higher redshifts, the PAHs start entering the wavelength coverage of PRIMA, as well as multiple far infrared lines that can be used as diagnostics for the metallicity amount of metals in the ISM of galaxies. So first of all, and these two, sorry, I forgot, the main science questions to answer are, first, how do PAH metallicity evolve throughout cosmic time from redshift 0 to cosmic noon? And then the second one is, when did the first PAHs arrive? Can we observe PAHs in the most distant massive galaxies? A little bit about PAHs. Why do we care about PAHs? PAHs are these molecules, large molecules, sheets of carbon with edges of hydrogen. You can call them large molecules or very small grains. They absorb single UV photons and get transiently heated to high temperatures, and as a result emit in the mid-infrared. The mid-infrared spectra, these broad features are as a result of bendings or vibrations in the carbon-carbon or carbon-hydrogen bonds of these molecules. The strongest of them is the emission at 7.7 micron, which you have heard probably the most as a star formation rate indicator at high redshifts. These molecules have significant roles in the heating and cooling of the ISM. In addition to that, in massive galaxies, they can account for up to 10% of the total dust mass of the galaxy, as well as 20% of the total infrared luminosity. So these two considered are much larger contributions than all of the other far infrared emission lines combined. As a result, PAHs are potentially very powerful tracers of star formation, but also molecular gas in galaxies. And their abundance depend on the metallicity and radiation field of the galaxy, which means they are also very good diagnostics for understanding the properties of the ISM that they live in. So particularly the PAH metallicity relation that I'm going to talk about, it has been studied extensively at redshift 0. According to this relation, the relative abundance of PAHs compared to the larger dust grains changes as a function of metallicity. At lower metallicities, the PAH fraction is low. On this plot on the right, the metallicity is in the opposite direction. So high metallicity is here and low in this section. And once you get above a certain metallicity threshold, the PAH fraction increases to higher values. This relationship has been studied extensively to understand the formation and destruction processes of these small dust grains, whether they are preferentially destroyed at low metallicities or it's a lack of their production that we don't see them at low metallicities. But at higher redshifts, at cosmic noon, there has been very limited few studies that statistically could look at this relation. This study that we did a few years ago is one of the largest that look at the PAH luminosity intensity as a function of metallicity, but it's based on Spitzer data, which was a single band observation. So very limited in terms of understanding the exact strength of PAHs. With Miriam JWST, you can start conducting such studies of PAH fraction as a function of metallicity, where metallicity is coming from the optical lines. But the statistics, as you can see, are very limited. What we really lack for these studies are large statistics and as well as unbiased metallicity indicators. So this is where PRIMA comes into play. PAHs can be observed with both instruments of PRIMA, the imager and also the spectroscopy. So with imager, as I mentioned before, the hyperspectral imaging from 25 to about 80 micron that provides a spectra basically of R of 10. Which can very nicely follow and reproduce the mid-infrared spectra of cosmic noon galaxies. Here you can see an example at redshift 2 and redshift 3 that is comparing two galaxies. One is star formation dominated, no AGN activity, and the other one has a significant AGN activity in it. So you can see that with the hyperspectral imaging, the PAH emission can be accurately recovered. This is with the photometry. Also with the spectroscopy, of course, you can look at the PAH spectra at cosmic noon and beyond. I will talk about the higher redshift ones later in the talk, but at cosmic noon, the strength of spectroscopy for PAH studies is that you can look at different PAH band ratios, particularly at cosmic noon. This is the first spectra you see here is redshift 2 and then redshift 3. At redshift 2, you can look at the longer PAH bands, 11 and 12 micron and beyond. And then at higher redshifts, you get to study the 7.7 micron again. This is a simulation from Unital 2025 that shows the sensitivity of the virus for 1 hour, 5 sigma sensitivity lines for 1 hour and 10-hour observations. And you can see that, and this is a galaxy with IR luminosity of 10 to 12. And you can see that you can easily measure the PAH emissions with a 10-hour observation or even with a 1-hour observation. With virus, in addition to looking at the PAHs at cosmic noon, we can also look at the fine structure far infrared metallicity indicators. Why this matters? This study very nicely shows the importance of using far infrared lines as metallicity indicators. This is the mass metallicity relation for local ULERGs that are comparing, and it's comparing the metallicities that are derived from optical lines. These are crosses, compared to far infrared lines. So these optical metallicity measurements have in the past placed ULERGs substantially below the mass metallicity relation for star-forming galaxies. While if we look at the dust unbiased far infrared lines, they bring the ULERGs back to the mass metallicity relation. So the point here is that for dusty massive galaxies, which are common at cosmic noon and actually are the ones that we're going to observe their PAHs with PRIMA, having far infrared lines to measure their metallicities as an unbiased indicator is extremely important and essential. So this brings us back again to what PRIMA can do at cosmic noon. This plot from one of the geoscience cases in the geoscience book, the second volume of geoscience book, shows beautifully how with PRIMA as cosmic noon, we have simultaneous coverage of multiple PAH lines. These are the dashed, PAHs are the dashed lines, and multiple far infrared lines. While this is the focus of the PI science case, there is also a lot of synergy with JWST MIRI that can be done together. And I'm not going to talk about that, but just wanted to mention that one of the the shorter half-an-hour talks next month would be by Leonor Ariscado, who's a PhD student at CAP, on this science case of synergies of MIRI and PRIMA to study the PAH metallicity relation at high redshifts. Back to the PI science case. So the idea is with this capability of studying PAHs and far infrared lines at the same time for cosmic noon galaxies, we're going to study the PAH metallicity relation for about 100 galaxies at cosmic noon. Yeah, as I mentioned, to measure the gas phase abundances using oxygen and nitrogen lines and the PAH mass fraction from 11 and 12 micron bands. And here is you can see the simulated PRIMA data for, and on the right, the detailed spectra for two scenarios of a low PAH fraction, galaxy with a low PAH fraction, and another one with a high PAH fraction. On the left, you see the PAH metallicity relation for local galaxies. And with PRIMA, with the largest statistics that we are going to get, we will study whether this relation holds at redshift 2 or whether it changes its metallicity threshold or its shape in general at high redshifts. And all of that would be even more powerful if we consider the survey capabilities of PRIMA. So here I want to pause. I want to spend a few slides on talking about the sky surveys that is going to be done with PRIMA and their amazing legacy value that will be there for the community. So these two histograms show the number counts of galaxies that will be detected with two survey strategies, deep survey and wide survey. These are both 1500-hour surveys on the sky. The deep is going to spend all these 1500 hours in a 1 degree square patch of the sky, and that's the histogram on the top. And the wide survey is going to spend the 1500 hour on 10 square degrees on the sky. Different colors show the number of detected galaxies with signal to noise of greater than 5 in at least 6 bands out of the 12 bands of the premature hyperspectral filters. At different luminosities. So from hyperlyrics in blue all the way to galaxies with higher luminosity of less than 11. So you have the whole range of lyrics, geolyrics, and hyperlyrics. And looking at these simulations, both of the surveys can detect the very most luminous galaxies out to very high redshifts. So the very obscured massive galaxies out to redshift 7 and 8 will be detected in these surveys. As a comparison for the rest of the population, you can imagine that with Herschel, we could reach to the infrared luminosity of 11 only below redshift of 1. You can very clearly see the power of PRIMA over Herschel, and think about all the amazing science that had been done with Herschel and how much we can build and expand those with PRIMA. So just as some numbers, the two surveys will give us full infrared SEDs for tens of thousands of galaxies down to the characteristic luminosity at each redshift. And then using this large sample of galaxies, we can do follow-up spectroscopic observations for many of them at cosmic noon, which I will talk in a second. Just before that, thinking a little bit more about what kind of galaxies we are detecting in these surveys. This is showing the star formation rate as a function of redshift, and the curves are the detectability limits with PRIMA. So while the orange one is 5 sigma coming from the confusion limit of PRIMA, with prior catalogs, we can go much deeper than the nominal confusion limit. And given that these surveys will be done on parts of the sky with a lot of ancillary data, this is very promising to know that with priors, you can go down to as much as an order of magnitude 1 dex lower sensitivity. The dashed line, if you're curious about the details, the dashed line is modeled with a prior catalog of just a positional prior. So you only know the location of the galaxies, the position of the galaxies in your image from shorter wavelength observations. While the pink one, in addition to the positional prior, you have a very weak flux estimate of each galaxy as well, which can come from SED modeling using available ancillary data in the field. But even with that weak flux prior, you can see that, especially at longer wavelengths where confusion is dominating, that helps a lot to beat the confusion and go down to star formation rate values at each redshift that are representative of the general population of galaxies that produce the obscured star formation rate. So this is very powerful, and as I mentioned, with these number statistics, large catalogs of far infrared detected galaxies, we can do follow-up observations using FIRIS spectroscopy. So here, this diagram is showing the redshift distribution of galaxies with N3 57 micron line and either at least one of the two O3 lines that are above flux limit of 10 to minus 19 watt per meter square. These far infrared lines, as I briefly mentioned before, they are very powerful diagnostics for dust, gas, metallicity, and as well as outflows in obscured systems. So the color histograms show the number counts of these galaxies with these lines according to simulations. The dashed histograms show how many of them will be detected in the deep and wide survey. And this gray rectangle here is the wavelength coverage that FIRIS can access these lines for follow-up observations. So again, all of this, both the photometric survey and the follow-up spectroscopic observations are going to be an amazing legacy for the community for all sorts of not only studying the far infrared properties of galaxies, but also using them for follow-up observations with multi-wavelength telescopes across redshifts. So aside from cosmic noon studies that I've been focused on, PRIMA is also going to be revolutionary in discovering dust in form of PAHs at very high redshifts. So these are two studies, as an example, that have simulated mid-infrared spectra for galaxies at a much higher redshift. On the left is redshift 4.6 for a very bright dusty galaxy, IR luminosity of 13. And on the right, you see the same galaxy with about the same luminosity, but redshifted from redshift 2 all the way to 10. So the takeaway point here is that a galaxy with 10 to 12 solar luminosity can be detected with PRIMA in a 10-hour integration with FIRIS. And if you want to go to higher redshift, a more luminous infrared luminous galaxy can be potentially detected. And this is very exciting because it will tell us whether we can have carbonaceous or we have carbonaceous grains in dusty systems in very early cosmic times. And with that, I'm going to my summary slide. So in conclusion, as a summary, PRIMA will use fast, sensitive, wide field infrared imaging, spectroscopy, and polarimetry to uncover obscured star formation and reveal how dust, metals, gas, and galaxies co-evolved from the early universe to today. Particularly the science cases that I showed. The first one was about dust grain composition and structure that are still open questions. By measuring the polarization spectrum in the local universe over a range of metallicities, PRIMA will constrain the evolution of dust from pristine stardust to ISM mixed dust. Then the other science goal that I talked about was to understand the origin and evolution of dust and metals, the co-evolution of dust and metals, particularly how they co-evolved over the past 10 million years and how dust was produced and processed in the early universe. For this science case, at redshift 0, PRIMA can measure multiple far infrared lines to calibrate far infrared metallicities with existing measurements from optical lines and PAH emission. At cosmic noon, PRIMA will be able to simultaneously measure the PAH emission and far-infrared metal lines in galaxies and look into the PAH metallicity relationship and its evolution compared to redshift 0. And at higher redshifts, it will measure PAH emission in the dusty systems to constrain the rise of dust. And last but not least, PRIMA can move our field from looking at individual dusty galaxies to statistically large populations. And this is thanks to surveys such as the deep and wide concepts that I mentioned, plus spectroscopic follow-ups that will characterize the dust and metals in these obscured systems at cosmic noon and beyond. Thank you.
All right, thank you so much, Irene. We have an opportunity now for questions from the audience. So you can feel free to put your question in the chat or go ahead and just raise your hand. Yes, go ahead, Margaret.
Very, very nice talk, Irene. I enjoyed it very much. So you kind of gave a good sweep of everything that PRIMA might do. What excites you personally the most? What would you most want to pursue?
So in the discovery space, I think looking for dust emission in the very high redshift galaxies is what excites me the most. So I mentioned here the PAHs, but not only PAHs, also looking at just dust continuum detection in the very high redshift galaxies. I think that would be amazing. With the current facilities, like with ALMA and NOEMA, we are trying really to go deep and find these, and it's an exciting area, and PRIMA can contribute a lot because the dust formation in at those very early times can provide very stringent constraints on how dust has formed, simply because of the time scale. There hasn't been much time to do a lot of ISM mixing. So the detection of dust, first just the detection, but also if there are multi-wavelength observations to look at the properties, for example, if there are PAHs, that would, I think, bring a very interesting constraints on what kind of dust could have formed and what should have been the channels that kind of dust could form in such short time scales.
Thank you.
Going to see. Yes. I think everything was very clear, and everyone is super excited about looking at dust at local and high redshift with PRIMA.
Yeah, no, thank you so much, Irene. It was a really wonderful and detailed talk. JD.
Yeah, I agree. Really amazing job. I loved it, Irene. As someone who's been, looking at these cases and building them for, going on 4 years or something now, seeing it through fresh eyes like that, I mean, it just adds to our excitement. So I wanted to ask you about the synergy. I know you mentioned there's going to be a talk next month describing sort of synergy between JWST and PRIMA at Cosmic Noon, where they sort of meet in the middle. What do you think is the sort of strongest aspect of that? Obviously, they're very different machines. They have very different capabilities. How do you think those two can be brought together fruitfully?
Something that I think would be very interesting, but I haven't dig too much deep into the numbers of sensitivity, etc. But would be very interesting, I think, as a synergy is looking at different. So the redshift that these two can complement each other to study PAHs. It's a very like small redshift range of like around maybe 1. But that's where you can get shorter wavelength PAH bands with MIRI and the longer wavelength PAH bands with PRIMA. And I think the combination of those two is the opportunity to study the PAH band ratios at cosmic noon, which we cannot at all do with any other facility or any other combination. And like there is a lot to learn. For example, with PRIMA, if we get the PAH 11 micron, there's a lot to learn with that combined with the shorter PAH bands 3 micron, the 7 micron about the size and charge distribution. Yeah, I think that would be interesting for me.
Thanks.
Great. We have another question from Georgia.
Yeah, hi, Irene. I'm curious about the polarimetry, actually. Do you know if it's possible to place constraints on the polarization of the PAH lines with perimeter? Or is it just too broad a band?
So when I was making these slides, I told myself that any polarimetry question, hopefully Brandon will be online to answer, because it's not really my field of...
I'm here if you want me to take it.
Okay. Yes, please.
So the PRIMA polarization is in 4 broad bands between 90 and 250 microns. So we aren't really set up to do polarimetry of the pH emission features unless they are very, very redshifted, and I think polarization would be really, really hard then. So unfortunately, I don't think that's something that we're going to be able to tackle.
Okay, still exciting.
So I wanted to ask Irene a little bit, following up on JD's question about synergies with sort of JWST and PRIMA. Some of the JWST stuff, it's sort of like you have to do this now before PRIMA launches. But I wanted to ask about ALMA in particular, because we sort of hope that it will still be around, and maybe by 2040 we have some sort of upgrade opportunity. So what sort of synergies do you see with the two of those essentially being able to operate in tandem?
With those two, there is a lot of synergy. So the like one of the, for example, follow-up scenarios that can be done with the large sky surveys of PRIMA is go and look at the ALMA coverage of it, or detect them, look at them in ALMA. So for example, at cosmic noon or around redshift 3, we have PAHs from PRIMA, and then with ALMA looking at the general dust temperature and far infrared dust emission. That would bring a complete picture of dust in a galaxy. And I think it would be much the advantage of having PRIMA in addition to bringing the pH flux is that ALMA field of view is very small, so you cannot do these kind of large surveys. So as a follow-up, it would be just a perfect match of like selecting galaxies based on the PRIMA observations and then go after them over some parameter space that is interesting, follow them up for detecting dust emission, colder dust emission with ALMA.
Thank you so much. Any last questions? All right. If not, thank you again so much, Irene. It was really a pleasure to have your talk today. And please join us again next month for our next series of talks, including, as we said, sort of more detail in the follow-up of JWST with PRIMA. And as a reminder, today's talk will be posted online. So any folks that you know who weren't able to make it, please always check out our YouTube channel for past PCAST talks. Thank you, everyone.
Thank you. Thanks, everyone.
Bye. Thank you.